All right, so 5.3 is where we are. So for solving trig equation, what I want to do, or what we're going to do is I'm going to start. I'll give you some kind of big picture guidelines, and then we're just going to go through a bunch of examples of different types of equations and the procedures that we're going to use to solve them. So we're using all of our algebra techniques. That we already know. So we might factor, we might add or subtract something from both sides of the equation. We might divide the equation by something. All of those kinds of things that we've used to solve equations before in algebra, we're going to use all of those techniques again. But we're going to add all of our new trig techniques. So we may be using identities. We will definitely be using our knowledge of the unit circle, using our knowledge of the relationships between various trig functions. So we're going to add all of those pieces into solving our equations. In general, and this is like working with identities, it's not a hard and fast rule. It's not every single time you solve an equation you're going to do this kind of thing. But in general, we want to isolate the trig function, and I'm going to put an S in parentheses, functions on one side of the equation. So just like we've done in the past with our algebra techniques, we want to get x on one side of the equation, or we want to get x squared on one side of the equation. And that's, in general, that's how we approach solving equations. And then, in order to solve this, we're going to find all angles that make the equation true. Including coterminal angles. So that's one thing that is different, definitely different about trig equations than most algebra equations. With algebra equations, we might get one or two solutions. With trig equations, all the coterminal angles are going to be solutions. So every time we go around the circle another time, get back to the same place, we get a new solution. All right, so what I want to do is just go through, we'll start basic and kind of build up our not our difficulty, but just build up the different types of equations and show how we're going to apply these ideas to solving trig equations. All right, so we're good with the big ideas here. Okay, so on all of these examples we're going to solve. So the first one, 1 minus 2 cosine x equals 0. That would be a trig equation that we might need to solve. So I'm going to get the trig function by itself on one side of the equation. So I'm going to subtract 1 and then divide by -2. So I get cosine x equals 1/2. Now I have my trig function by itself, and now I say, okay, I need to find all the angles that have a cosine of 1/2. So now we have a unit circle problem. So we're going to say x equals, so what's an angle What's an angle with a cosine of 1/2? Pi thirds. There we go. Have to get pi over 3, and all the coterminal angles with pi over 3. So I'm going to say plus 2n pi, where n is 0, plus or minus 1, plus or minus 2, dot, dot, dot. Now, we don't have to write this every time. We're just saying that we have a multiple of 2 pi. We can add any multiple of 2 pi, and we get back around to pi thirds. Another angle with a cosine of 1/2. So we have, what is it? So yeah, we don't. So that would be the magnitude would be 1/2. Negative pi thirds. Negative pi thirds, and usually we go around for these solutions we want to go around counterclockwise. So negative pi thirds is the same as 5 pi thirds. And then we'd say plus 2n pi. So those would be our solutions to this equation. All right, questions? Now, if the problem had asked us just to find the solutions between 0 and 2 pi, we could just say pi thirds and 5 pi thirds. But if it said find all the solutions, we want to add all these coterminal angles. All right, let's look at another one. We have sine x plus 1 equals negative sine x. So that's our equation. So I want to isolate my trig function. So I'm going to add sine x to both sides. So I get 2 sine x plus 1 equals 0. And now I can subtract 1 and divide by 2. Sine x equals negative 1/2. So now we say where on the unit circle, what angles on the unit circle give us a sine of negative 1/2. So our y coordinate has to be negative, so we have to be over here in the third quadrant, or over here in the fourth quadrant. And the y coordinate is 1/2, so we're talking about the short side. Is that right? 7 pi over 6? I think that works. 7 pi over 6 would give us a sine of negative 1/2, and we'd say plus 2n pi. And then what's the one over in the fourth quadrant? Yeah? 11 pi over 6. So those are our solutions to that. We could say, and for this one we could say negative pi over 6. It's not incorrect. Usually you'll see the answers written in terms of our standard unit circle angles. And also notice that we're not using inverse trig functions to solve these equations. We're not saying we want the inverse sine of negative 1/2. We want every angle whose sine is negative 1/2. All right, questions there? Okay, let's do one slightly different now. Tangent squared x minus 3 equals 0. So we want to solve that. So we're going to isolate the trig function. Tangent squared x equals 3. We want to get tangent x, so we say tangent x equals, I'm going to take the square root. And when we take square roots to solve equations, what do we need to include? Plus or minus. Tangent x equals plus or minus square root of 3. So now we have a unit circle problem. We say where on the unit circle is our tangent equal to plus or minus square root of 3? Pi over 3. And because the period of the tangent function is pi units, tangent repeats every pi units, we're going to say plus n pi. And we have a plus or minus square root of 3. So what are our other possible angles? Don't we get all the pi thirds angles for our tangent, where our tangent is plus or minus the square root of 3? So I could say 2 pi over 3 plus n pi. X equals, what's our next one? 4 pi over 3. And x equals 5 pi over 3. For problems like this, your book, in the book, it would only list these two answers. And here's why. If we look at our unit circle, and we're here at pi over 3, and we add pi radians, where do we end up? We end up at 4 pi over 3. And if we're here at 2 pi over 3, and we add pi radians, we end up over here at 5 pi over 3. So these two would include the other two solutions. It is not incorrect to list all four, but just be aware that if you look up the answer, you try a problem and you look up the answer in the book, it might only list 2 of them, especially for the tangents and cotangents. And that's why, because when we add pi, we get to one of the other ones. All right, questions on that example? Okay, let's make it a little more interesting. So for this one, we want to solve secant x, cosecant x equals cosecant x. All right, and I'm going to say for problems like this, you do not want to divide both sides by cosecant x. And that's the same reason you would not want to, how do I want to write this? If we had an equation like this, if we divide both sides by x, what are we assuming about x? Since we're dividing by it, what are we assuming about x? That it's not 0. But could x possibly be 0 and solve this equation? Yeah. So if we divided by 0, we would lose that solution. And we'd also be technically dividing by 0. So what we want to do here is subtract x from both sides. So we just end up with x squared. So we're going to do the same thing here. We're going to do secant x, cosecant x minus cosecant x equals 0. Now what if we had, so what I'm going to do is, say if we had an equation like this, how do we go about solving an equation like this? Factor, we're going to factor. We're going to do the same thing here. Factor that common term of cosecant x. Because what we would do here is say x times x minus 1 equals 0. Same thing here. When we have an equation like this, now what do we do to solve this? What's the only way two numbers can multiply and give us 0? What does one of them have to be? 0. So this, we set each of these. This is like when we have two sets of parentheses. We're going to say cosecant x equals 0 or secant x minus 1 equals 0. So we split this into two possibilities. Well, this is saying 1 over sine x equals 0. Is 1 over sine x ever equal to 0? No. So this one gives us no solution. Now it won't always turn out, so this one, it would be, it turns out that cosecant x is not 0, but it doesn't always turn out that way in terms of, not that cosecant x is not 0, but that we can get a 0 as our solution. And here we're going to say the secant x equals 1. Well, that tells us 1 over cosine x equals 1. So 1 over cosine x equals 1 when cosine x equals 1. So now we go to the unit circle and we say, when is cosine x equal to 1? X equals, what is it? For a cosine? X squared is 1. So 0. So we could say 0 plus 2n pi. And that would be our solution. Some multiple of 2 pi. All right. Questions on that example? And you could, for this answer, you could just write 2n pi. You don't have to write the 0 plus. All right. Well, let's go to a slightly different type of equation. These are kind of linear equations. Let's go to quadratic equations. 2 cosine squared x, whoops, not 2 x's, 2 cosine squared x plus cosine x minus 1 equals 0. And we want to solve this. We can think of this one. We did some simplifying of these types of expressions that we have on the left here. We can think of this just like we think of 2x squared plus x minus 1 equals 0. How would we solve that? Factor. And we're going to factor this exactly the same way. So I'm going to say this is a 2 cosine x, and that has to be a 1. A cosine x, and that has to be a 1. And what do we have to have? A plus and a minus to get my 1 cosine x term there in the middle. I think I did that right. And now we're going to do exactly like we did on the last one. When we have two things multiplied together that equal 0, one or the other of them has to equal 0. So this says 2 cosine x minus 1 equals 0, or cosine x plus 1 equals 0. Exactly like we would do here when we got 2x minus 1 and x plus 1 equals 0. We'd say 2x minus 1 equals 0 or x plus 1 equals 0. Same thing here. Well, this tells us that cosine x equals 1/2 or cosine x equals -1. Didn't we already do this one? Wasn't that our first example? Cosine x equals 1/2, so we get pi thirds and 5 pi thirds for our answers. And 5 pi thirds. And here we want to know where on the unit circle what angle gives us a cosine of -1? Pi. And all the coterminal angles. And your book will write this one as 2n plus 1 pi. So they'll factor out that pi. This is fine, but you'll see it written like this. If we distributed the pi, we get exactly that. So this tells us that we have odd multiples of pi. So we get three answers and their coterminal angles out of this equation. All right, questions? Okay, well, there's one. So we got a couple more, just a couple more things to talk about. But one thing we haven't done so far is we haven't gotten to use any identities. So let's look at another example that's a little different. Again, quadratic equation. Well, what's our issue here? We have cosines and sines, and we don't have any common factors that we could factor out like we did the example 2 examples ago. But what do we have? We have a cosine squared. We have a nice relationship between cosine squared and sine squared. So we can use an identity. So I'm going to write cosine squared as 2 times 1 minus sine squared x. So I have 2 minus 2 sine squared x plus 3 sine x minus 3 equals 0. Now we just have signs involved here. So let me combine like terms, and we get -2 sine squared x plus 3 sine x minus 1 equals 0. We could factor from here. That would be fine. I don't like that leading coefficient to be negative. Just personal preference. So what can we do? Well, if we remember when we have a quadratic equation, we always want everything on one side and 0 on the other side. Can I just multiply everything by -1? Because if I multiply 0 by -1, it doesn't change anything. So I can multiply both sides of the equation by -1 and still have the same equation. And now we're going to factor, just like we did on the last one. So I have to have a 2 sine x and a 1 and a sine x and a 1. And do I need a negative and a negative? I believe, for our factoring. And now we can split this up. I get that sine x has to equal 1/2, or sine x equals 1. And now we go to the unit circle and we say, when is sine x equal to 1/2? Pi over 6, nice. Plus 2n pi. And what else? So we're here in the first quadrant. We need the fourth quadrant angle there. 11 pi over 6. To give us a sine of 1/2. Is that right? Yeah, it'd be 5 pi over 6, wouldn't it? Sine of 11 pi over 6 is negative 1/2. There we go. Sine x equals 1. Pi over 2 plus 2n pi. So those are our answers. Those are our solutions to that equation. All right, questions there? All right, one more type of equation that we need to talk about, slightly different than these, and I'm going to kind of work two problems in parallel. We need to talk about multiple angles. And the solution, the method for solving these multiple angle equations is exactly the same, except for one step at the very end. So we might see a problem that looks like this. So here we have a 2t, or we might see something like cotangent of x over 2 plus 1 equals 0. So we might have, and we could have our angles multiplied by something other than 2 or divided by something other than 2, but the method's the same. So we're going to go through the same steps. We're going to get our trig function by itself. So I'm going to say sine of 2t equals negative 1/2. Here I would say cotangent of x over 2 equals negative 1. So here we want to say our angle is 2t. So we say, where on the unit circle do we get a sine of negative 1/2? Didn't we already do that one? There we go. Sine x, 7 pi over 6 or 11 pi over 6. So I'm going to say 2t equals 7 pi over 6 plus 2n pi, or 2t equals 11 pi over 6 plus 2n pi. But we want to solve for t, not 2t. So now I'm going to divide everything by 2. So t equals 7 pi over 12 plus n pi. Or t equals 11 pi over 12 plus n pi. And we'll do this other one in just a second. But let's think for a second about what this sine of 2t does to the graph. What does it do? What does that 2 do to the graph? It changes the period, right? Makes a period pi instead of 2 pi. So you're going to get your graph, you're going to get more ups and downs in your graph in the interval of 2 pi. 7 pi over 12 is smaller than 7 pi over 6, so you're going to get more of those in the interval from 0 to 2 pi than you would have otherwise. So you get more solutions. These are smaller numbers, so you get more of them between 0 and 2 pi. So that makes sense. All right, for this one, cotangent of x over 2 equals negative 1. So now we think about the unit circle, and we say, when is our cotangent equal to negative 1? So that's where the sine and the cosine have the same value, but one is positive and one is negative. Three pi over 4. And plus an n pi, because a period of cotangent is pi. And what's another one where our tangent or tangent, sine, cosine are the same value but opposite signs? 7 pi over 4. plus n pi. Well, we want to solve for x. So now I just multiply everything by 2. So I get 3 pi over 2 plus 2n pi. And x equals 7 pi over 2 plus 2n pi. And that makes sense here because the dividing by 2 makes the period longer, so you should get less solutions in the same interval. Well, these numbers are bigger, so less of them are going to fit between 0 and 2 pi. So the only difference with multiple angle equations is this last step where you either have to multiply or divide by whatever your angle is being multiplied or divided by. The problem-solving procedure is exactly the same up to that point. All right, questions? Okay. All right, there's that. And